Hello, ladies and gentlemen. I am very happy to be speaking with you today. My name is Cherroun Rima. I am a doctor in physics at Mohammed Khaydar Biskra University. Today I am here to talking to you about effects of substituting IZTO with graphene in beta-gallium oxide solar plant Schottky ultraviolet photodetectors. My presentation is divided into 5 sections: an introduction, device structure and modeling. Then we will take an overview of Silvaco Atlas, and finally we will discuss the simulation result and give conclusion. So let's take introduction. Deep ultraviolet photodetector uses wideband gap semiconductor like GaN, carbide silicon, ZNMG offer nuclear solar planets and low direct current due to their wideband gap, low permittivity and high radiation resistance. Gallium oxide has 6 polymorph: alpha, beta, gamma, delta, epsilon and K. Monoclinic beta gallium oxide is the most stable polymorph and ideal for solar plant UV detector due to its wideband gap 4.7 to 4.9 electronvolt, which enable absorption below 280 nanometer with a high absorption coefficient better 10 power 5 cm-1. It's also offer low grey ghost, radiation hardness and stability. Beta gallium oxide is promising power and high voltage electronic device material with a critical field exceeding 8 megavolt cm-1. Additionally, beta gallium oxide device exhibit low conduction losses and high power conversion efficiency, key feature for high voltage and high power. Now we will move to a device structure and modeling. Schottky UV photodetector was fabricated onto a 650 micrometer thick 4HSEC substrate with a doping concentration 10 power 80 cm-3. Beta gallium oxide doped with Se drift layer with doping concentration 3 times 10 power 60 cm-1. ETO as amic contact, while IZTO as Schottky contact. The input material parameter and the input traps parameter is the simulation process. I'll review of Silvaco Atlas. Silvaco Atlas is physically based 2 and 3 dimensional device simulator that predicts the electrical behavior of semiconductor device at specific wise condition. The order Atlas commands start with instruction specification, after that material model specification, following by numerical method selection and solution specification, and the last one presents the result and analysis. Now to move to result and discussion. Figure 1 illustrates the GV characteristic and the reverse and forward bias for the both case graphene and IZTO as Schottky contacts at 255 nanometer wavelength and the dark condition. When graphene Schottky contact is used, instant IZTO contact enhancement are observed in both dark and light condition. In the dark case, the forward current increasing significantly while the reverse current decreasing, causing a substantial rise in the PDCR to around 10.5. The insertion in graphene has significant enhanced light detection sensitivity are demonstrated in figure 2 and B. A and B, both EQE and responsivity increasing. The rejection ratio and the detectivity also improved. Shift values of 2 times 10 power 3 and 5 times 10 power 12 joules at -1 volt and 255 nanometer. Figure 3 shows the time-dependent photoresponse using graphene and IZTO Schottky contact at -1 volt and 255 nanometer wavelength. The photocurrent density by using the graphene Schottky contact reached remarkably 52 microampere cm-1 at t equals 0 second, surpassing the IZTO Schottky contact. This increasing did not impact the rise and decay time, which are nearly identical IZTO Schottky contact. As shown in figure 4, A and B present the photocurrent responsivity and EQE versus light power density, compared IZTO and graphene at -1 volt and 255 nanometer. For the both case show the same onset detection threshold. However, all optical outputs, photocurrent and responsivity and EQE, demonstrated better performance with graphene Schottky contacts. Now we will study the investigate of work function of graphene in device performance and the 255 nanometer illumination EV curve figure 5A and band energy figure 5B for the work function 4.1 and 4.2 overlap significantly, showing increasing photocurrents and positive GV shape resulting from the reducing Schottky barrier between graphene and beta-gallium oxide SE drift layer, and figure 5C corroborating this finding. Now I will conclude my research with action. Replacing IZTO contacts with graphene contacts results in improved performance under both dark and illuminated conditions. However, all optical outputs including photocurrent, responsivity and EQE improvement with the graphene Schottky contacts and increased the graphene work function, enhanced the photocurrent and causing the positive shape in the GV characteristic attributed to the reducing Schottky barrier at the graphene and beta-gallium oxide SE drift layer interface. Thank you for your attention.